When doing 3D deep learning, it may be useful to visualize your results. One of the reasons you might do that is to verify that the output of your model looks correct for whatever your training might be. You can also debug issues. You can see that a loss value is going down, but perhaps the final loss value isn't low enough, and so visualizing the result to see how it looks may be helpful. And finally, you may be able to observe interesting patterns in the output that, for instance, if you're doing implicit representation, you can look at interesting frequency analysis for the output compared to the ground truth. Or if you're doing super resolution, you can see if there's any kind of artifacts involved. And so this is all very useful to do on 3D data. All of this already exists in 2D with something called tensorboard. Let me move myself over here. For instance, you can log your training stats like your GPU memory that you're using during training and the loss value over training. In this case, there were 2 runs when it was when I ran the tensorboard script, so it kind of has this jagged line. But normally they look more like nope, not even like that. They're both bad. In any case, doing this, we can also visualize the reconstruction over time. So this is again an implicit model. It's training to fit this ground truth over some number of iterations. And so we can observe that in the beginning it's very coarse, and as the steps increase, it's learning the finer and finer details. This is using a siren model for an example. And so this is nice. This already exists in 2D, and we can even make custom 3D apps to do this as well. Let me run the code for this real quick. So this will be loading the exact same model that you just saw in TensorBoard. This is the full resolution reconstruction. I've made a little small web app to be able to, what was the solution to this? I forget. Fix bug, there we go. To like select a small region, you can select a crop and verify that even this small area looks good. We can do super resolution on this crop to see how well the network is interpolating. Is it adding any high frequency features that maybe we don't want between the pixel values, etc. So this is like a live way to check how well your model is fitting the underlying data. This is useful especially for like these smaller areas, these higher frequency details. Looks like this might be a lake or something in the background. This might be a reflection. And we see this kind of x-axis higher frequency detail that this network doesn't capture very well, that maybe you would have overlooked in the original photo, but now we can kind of scan and sweep across the entire image. And we also see some boundary artifacts, for instance, here. And so we can do this in 2D, and we can also do this for a slice of 3D data. I don't have great data for this right now, but these data are very minimal. But we can only do it for a slice of the 3D data if we were to use an app like that. So something more useful would be a volume renderer like this. To visualize 3D scientific data specifically, a volume renderer and many algorithms for the volume rendering are useful. For instance, this right here is just called direct volume rendering, but there's also isosurface extraction. You can do particle tracing in vector fields, so on and so forth. So there's a lot of ways to visualize your volume, especially if I just show you here. There's many different kind of algorithms to take a different look into the same volume that may be useful to scientists especially. But if we're training a 3D model, it's also useful for machine learning practitioners. So I'm going to show you how to create or how to use Paraview. In this case, Paraview is a open source volume renderer, software renderer, and it's been my go-to tool for any debugging, creating visualizations for papers, etc. Other research groups may have custom renderers for their own papers and needs, and different scientists may have different volume renderers for certain data types. But most of our data, the data that I'm using, is regular grid volumetric data, so it's 3D on a grid. So like images are a certain resolution, maybe 512 by 512 pixels. A volume can also be 512 by 512 by 512. So it's just 3D. Paraview here is very flexible. It fits to 2D, 3D, 4D, any dimensionality, time steps. It's very powerful, and I'm only going to show you a very small glimpse into what it can do. So first I'm going to show you the code to create the file that we will visualize. So this is the code in question, tensor to CDF right here. So CDF is it's actually called NetCDF. It's the format that we'll be using, just like there's PNG and JPEG. CDF is the file format that I use for visualizing in Paraview. It's very simple. It's actually a little bit more, it's more complicated than just writing a PNG. You have to do a little bit of back-end work. You have to first, let's take a look line by line. It's going to take tensor, save location, and if you want to have custom channel names, you can select channel names. I assume the tensor is in the shape that that a typical convolution network will output it as, where this first dimension is the batch size. I assume that there's no batch, it's just a batch size of 1. And then we have our channel dimension, and then we go depth, width, height. Or in the case of 2D, there's no height, and there's no third dimension. It should just be height and width. And actually, this might be backwards. The certain order of these is a mystery to me. Sometimes it can be inconsistent between different packages, and but like normally when you save an image, it goes height then width. So I think here I actually should be depth, height, width, or something along these lines. So it's Z, Y, X. And if in the case of 2D, it would be Y, X. So first, we create our data set at the location. This initializes the file, and we initialize it with write. This documentation for this CDF package, I'll scroll up to what package. This is actually called NetCDF 4. You can just install it with, oh, it's escaping me. apt-get, no. The pip, Python package manager. You can just install it with pip. And so yeah, that's where this dataset object comes from. We're going to create the dimensions for the dimensions that we have. So if we're in 3D, we add this Z dimension, and then we also have a list of our dimensions, X, Y, Z, or just X, Y if it's 2D. So this is just setting up the dimensionality of your data set. I'll add this. And these are just the spatial dimensions. The time dimension is a little different. I think it has to do with how you number and save your files. You can then load them in Paraview as a sequence for time steps. I won't go over that today. I'm not interested in that right now. And next, if you have channel names, you can ignore it, but if you don't, so for instance, it might be, someone might have already given you like U, V, W for vector field channel names. But in the case that they didn't, I just set the default to A, and it'll just incrementally go A, B, C, D for every channel in your data set to save. And then I iterate through each channel and set the channel name properly. This will just increase it to A, B, C, D, so on and so forth. Then we create a variable. So our data set, we create a variable for this channel, give it channel names. We tell it what data type it's going to be. I use float32 in all of my machine learning right now. And then the dimensions that this variable will lay in. So we can specify it can lay in any subset of the dimensions that we added. But in our case, they're all using all three. And then this is just setting, it's like a dictionary, the channel in this data set now. We're going to set all of that to the data here within that channel. And then I clone, detach CPU numpy just to bring it to the CPU, bring it to numpy format, which can go into here because it cannot read directly from the tensor. And that's it. That creates our CDF, and then we close it. That's pretty much the only code that we'll need. I'll call that in like a test script. I'll do this post hoc after training, just to create this output file to visualize. I don't do any visualization during training. I think that would be a bit too heavy because, for instance, this file, which is I think 512 by 512 by 128, it's a scalar field. There's only one channel. As I said, called channel data, but it's a scalar field, and saving one of these every X time steps would probably cause too much storage. End up costing gigabytes just for a single model to save the logs for this file type. And also there's no interactive visualization during training like there is with tensorboard. That might be something nice that, if someone ever adds that for 3D deep learning, that'd be fantastic. But let's go over how to actually do this visualization. So I'm going to use the same file. This is just a scalar field file. I have some output files here from a previous project. All I do is drag in the file that I want to visualize. So it ends with a .nc. That's what Paraview recognizes as a NetCDF file. And then I select this NetCDF reader. After that, it brings it in. It doesn't actually load it, but then after we click apply, that will finally load the volume, recognize the dimensions, and initialize everything. So it could take a second to load that data depending on how big it is. So like 124 cube data can take a few seconds depending on your machine. Note that this uses the GPU, so if you do have 1024 cube data, you need a decent bit of VRAM to save that in memory. So next is I changed the visualization type here from, it defaults to outline. I set that to the volume, and then initially you'll see something like this. I'll just reset this really quick. So for my data, initially I see something like this. On the right here is called the transfer function. This is mapping data, but this is the transfer function. This maps our data values to output colors. It defaults to this cool to warm value. These are the color scale on the bottom, and then in here we see the opacity value. So by clicking at any point in this area, we can create a new knot that we can change. And so for instance, I know in this data, a lot of this lower temperature area or lower velocity area is not interesting. So we actually just want to bring the opacity down for that lower area so we can focus more on this higher velocity data, and we can see more of the feature. For instance, at the bottom of the plume, it's a bit more complicated than what we could see when it was in the way from the low velocity data. So we can change that. There's also pre-made, if I click this little folder with the heart icon, these are favorites. These are presets for the color mapping. These will override the color mapping. So in this case, it changes the blue to red to this rainbow color format. There's many other color formats, and if you change this drop down from default to all, you'll see that there are many that are pre-built that may be useful to you in your specific application. You can also save your own presets. I do these when I'm writing a paper and I'm making visualizations, and I need to have a consistent mapping for different outputs from different data sets, or different outputs for different models for the same data set. So for instance, I think I use this visualization for this data for a few outputs. So yeah, you can make your transfer function as complicated as you want. You can add as many points as you want for the clarity of your output. So far, this has all just been for scalar fields, meaning volumetric output with only one channel or one variable. I'm going to reset this and delete all these. You can click on these and then click the delete button. That will delete each of these knots if you just want to reset back to the original. So here's the original. Something else you can do is add filters on these. So this is how we can get a little more complicated. If I go to alphabetical here and choose contour, these are isocontours or isosurfaces in 3D. Excuse me. And then down here we get to change that filter. So I'm going to first exit that. Then there's this range button. I click this range and it will automatically go from the minimum value to the maximum value, and it will linearly space 10 samples, and I'll just click generate. It'll create these samples. It doesn't actually do anything to the data yet, but after I click apply, then it creates this new visualization up here, right below the actual volume. And by the way, on the left, if you see these eyes, you can click on these eyes to show or hide any piece of data that's currently being visualized. So I'm going to hide the original volume and take a look at this. So right now we have this outer isosurface that's really not too interesting, so I'm actually just going to clear all of these, reset this, and I'm going to start my range at like 0.2 or something, you know, to ignore the lower values that I didn't care about. Okay, so now we get something that conforms more to the region of interest, I guess. We don't want that outer area of the volume. So this is more interesting, but we don't really get to see inside of the other isosurfaces. So we can add another filter. There's another one here. We can use clip. So in this clip, we can choose an axis that we're going to slice by. So for instance, if I want to slice on, you see this red rectangle here, we can slice on that axis, which will give us a view right down the middle. And now we can see inside of this data to see all these iso contours at the contour lines here, these contour iso values. Similarly, if we want to undo that, we can do Control Z, and then let's go on on another plane. If I do this and this, does that change the plane? Yep, there we go. So I've never done this before, but we can change the plane that we're working with. So in this case, going to work on a different plane. Actually, it's too similar to the other one we just did, so I'm going to change this to the last plane. We're going to take a view right in the middle. You can also move this, presumably left and right. So this is at value 250. If I move this to 200, it'll move it up. Okay, so let's take a look. Yeah, let's just look right there. We can see inside right there. Looks about like what we expect, just concentric circles. I'm going to undo that, and oh, that got changed. Set back to that 300, 350, and something interesting. I guess it's only showing that direction. If I change this to -1, I'm assuming that will show the other side. There you go. So many ways to use these, and you can layer these on top of each other. So we have a contour first, and then a clip, and you can even add more things on top of this. We can then do thresholds on that to remove some set of those lines. So now we're only looking at some of those ISO values. Yeah, so these can build on top of each other as much as they want. And you can show many of these at the same time. So actually I'm going to Control Z to bring that back. Actually I don't want that one, but I do want that one. And I'm going to add the clip. Do that. Okay, so back to this first visualization that we had. We can also change the color mapping while we're after all of these, by the way. So you can change this at any point. You can also change the range of these by sliding down the maximum and minimum values, and we can see how that adjusts the data. So now we're getting a bit more extreme. Undo that a little bit. Okay, and then you can visualize multiple volumes or multiple things at the same time. So I can turn this on top of this ISO contour extraction, but maybe it's a bit too dense or a bit too yeah, not as transparent as I'd like it to be. So I can bring it down a little bit, and we can see that the volume is still showing right there, but we can see these ISO contours a little bit better. Yes, there's a lot of things you can do to play with this kind of stuff, and get the visualization that you want. Built into Paraview, very handy, without much coding at all. Okay, so that's been scalar fields so far. Next thing I'm going to jump into is vector fields. So let me go back to my other project, output data. Okay, so I have a lot of output data here. Let's bring in Isabella. Same process, I just drag it in, click NetCDF, I'm going to remove my old data, and I'm going to hit apply. This one's a little bit bigger, so it took a little bit longer. Have it selected, and then I'm going to click volume. So this, by default, will visualize single channels one at a time. I've saved it. You can see your channels up here on the top left. I have U, V, and W. You see they're all visualized different. I can change the presets for any one of these, but something different is that Paraview will save the color mapping per channel. So right now, the entire U channel will be visualized like this, but V and W will remain in the original color space. And this is shared across many, all of the volumes that you have on the left side. Any volume that has a U channel name will change its visualization to be the exact same. You can isolate it by clicking this button here. There's a button down here that toggles, I'm sorry, this just hides the visibility. There's this button, I think, on the right, or one of these. Oh, here we go. Use separate color map. There's a button here. If you want this data to specifically have its own color map, you can unlink it from everything else and work on this by itself, and it won't change any other data with the same channel. But that's not necessary right now. But we don't need this. Go back to here. Okay. So this is the Isabelle data set. I'm actually going to visualize a slightly more simple data set right now. Let's get the synthetic VF3 original. Here we go. That's the normal. Do I have the original? Nope. Okay, we'll work with one then. So same thing here. I'm not sure why sometimes they show more options. Always just choose NetCDF reader. Apply. You don't have to visualize the volume first. I just like to do it to make sure it loaded it properly. And this is a pretty simple volume. This is from a particle. It's fluid data. It's 2 or 3 vortices meeting, and we can't really tell that just by looking at these scalar fields, right? We have no idea. This is a vector field, so we need a little bit more information to tell what's going on. So what we do is add a calculator filter first. This is responsible for joining the 3 variables that we have. So one channel is called A. I'm going to type A times I hat, because A is in the direction of I hat in physics, plus B times J hat, plus C times K hat. Type it in just like that. If you have UVW as your channel names, you'll name these UVW instead. And after that, you just click apply. This will create a new calculator, and this will have a new variable. It's going to have result. So this is essentially the magnitude. This is the vector magnitude at each spot. Magnitude right here. And next, what we want to do is do a stream tracer on this. This will allow us to visualize the streams. So it defaults to this. This is called a rake, and it'll evenly spaced particles on this. I prefer to use a point source, so it'll drop particles randomly in this circle. And I normally change the radius to be a little bit larger, so I do about half. I make my radius half of the volume, so that we can see that it fills in the entire volume. Okay, and then after that, all I do is click apply, and then it traces particles through your volume. It traces them backwards and forwards by default. We can see there's an option, yeah, both directions. We can go forward only or backward only. Thankfully, they do both, so we get a more clear picture. If you want to focus your particles just in one spot, like a smaller ball, we can really see where those particles are going. And you can move this ball around just on the screen interactively. But since this vector field is pretty simple, I just use a very large domain just to visualize how it goes through the entire volume. Yeah. yeah, so this is how I visualize my output from my neural networks. If I'm looking for the difference in the ground truth and a reconstructed volume, for instance, this data is the original data, but if I want to look at the output from my neural network, I can see how similar they are. So I have to go through the exact same process. I have to add filter, calculator, a times I hat plus c times k hat. Apply, add, stream tracer. I just do the exact same thing, change the point source and larger field. And then we can see if I toggle off the old one, which is up here, we can see that it's a very similar vector field. So we can see that our neural network did very well at reconstructing this vector field. Yeah, so that's all I have for visualizing 3D output from neural networks, whether it be a scalar field or a vector field. Paraview is very powerful and can be useful for either of these types and even more, such as time varying, but I haven't gone over that at all. Thank you.